Welcome to this AP Chem video about net ionic equations. This video is going to go through the worksheet that I gave you for homework and how to do examples and the problems that are in it. You should have by this point done the classwork activity on net ionic equations so that you understand the basis of why we do net ionic equations, why we write the equations that way. It's mostly to make sure that we're writing the only things that are going on inside the reaction at any particular time, ignoring the spectator ions. But in order to do that properly, you really should start with the balanced formula equation and then write the total ionic equation, which shows every single ion in the reaction, and then finally end up with the balanced net ionic equation, which just shows the ions that change when they become a different state of matter, or when they form bonds, or when they change charges. So we're going to go through this right now, starting with example number 3. I'm going to point out to you that example number 1 is done for you, and example number 2 is a pretty straightforward one, which is why I haven't done it. If you want to see a good example of just a basic net ionic equation problem, this might not be the best one for you. You should wait a little later in the video. In fact, if you're looking for one to turn to right away, you probably want to go to maybe number 7. You can just fast forward through the video to look at number 7 if you need some help with basic net ionic equations for double replacement reactions. This particular reaction includes magnesium, which is normally 2+, but since it's in the ribbon form, it means it's solid. It has no charges, magnesium 0, so don't put the 2+ down. Hydrochloric acid, just plain old HCl. Hydrogen's positive, chloride's negative, and if it's in water, which it probably is, it's aqueous. By the way, interestingly enough, hydrochloric acid can only be a gas at 100% concentration. Otherwise, it's aqueous. It's usually aqueous. Right. To write the balanced formula equation, you'll notice that magnesium here is reacting with hydrochloric acid. And this looks to me like a single replacement reaction. That's the type. So that means the magnesium is going to pair up with the chloride, and the hydrogen is going to be off on its own. But you know that magnesium should be 2+ and chloride should be 1- when it's in a compound, so that's going to make it MgCl2. It's aqueous according to the rules in the solubility chart up there. If it has chloride, it's probably going to be aqueous, soluble. And then the hydrogen has to be diatomic in a gas because it's alone. All right, that's the formula equation. We do need to balance it. There's 2 chlorines and 2 hydrogens on the product side, so we should have 2 in front of the HCl on the reactant side, and that balances all the atoms. The total ionic equation, well, magnesium is not an ion, but it should still be in the equation. Hydrochloric acid is made of ions. The hydrogens, when you put them in water, when they're aqueous, they're actually separated from the chlorides, and they're hanging out as the positive, the cation. And we should put the AQ after it for bookkeeping purposes. Chloride is now negative, but there's 2 of them because the 2 in front of the HCl originally. For every hydrogen, there's 1 chlorine, and this is aqueous. Magnesium chloride actually is ionic because it was soluble. So Mg is now 2+. It's, oops, I got to move that back. There we go. It's AQ, and there's 2 chlorides still, which are negative and aqueous, and the hydrogens are still hanging out as well, and they're gaseous. All right, you might notice that on the 2 sides of the equation, the 2 chlorides are hanging out on both sides, so they're not going to show up in the net ionic equation. However, the magnesium and the hydrogen will. The magnesium will because it's changing charge and changing state. It's turning from solid to aqueous. The hydrogen will because it's changing charge and changing state as well. It had a 1+ charge, and now it's going to become neutral after the reaction's over. So it's going to make magnesium solid plus the 2H2. It sticks around. The chlorides don't stick around. We're just going to cancel those out. And we form magnesium 2+, which is aqueous, and hydrogen, which is a gas. Right, a little preview of coming attractions here. Magnesium had a 0 charge, and now it has a 2 plus charge. Hydrogen had a plus charge, and now it has a 0 charge. So magnesium is actually what we call being oxidized here, and hydrogen's being reduced. This is actually a redox equation, and we're going to talk about that a little later. Let's go to the next equation. This is example number 5. I'm going to go through this one a little quicker. Magnesium is 2 plus with chloride, which is 1 minus, and calcium is 2 plus with nitrate, which is 1 minus. And they're solutions, which means they're both aqueous. We've got a crisscross to even out the charges, so that's going to be 2, and that's going to be 2. And so I can write the balanced formula equation. It's double replacement, so that's the type of this reaction, because we have two compounds, both ionic, and they're going to switch their partners. So when we do this problem, we're going to write down that magnesium chloride, which is aqueous, will react with calcium nitrate, which is also aqueous, and form, well, what will it form? Magnesium will switch to be paired with the nitrate, and the calcium will be paired with the chloride. As a result, it's going to be CaCl2, and then the other product is going to be MgNO3. All right. Interestingly enough, on the rules, magnesium is soluble, and nitrate, the calcium soluble because it's with chloride, magnesium soluble because it's with nitrate, no exceptions, which means these are both aqueous. Guess what that means? It means since everything's aqueous on both sides, there actually isn't going to be a balanced net ionic equation. There's essentially no reaction. However, just for completeness, we really should write this whole thing out here, just to show that there's not actually any reaction going on. By the way, did I balance it? Yeah, it's balanced. All right. There's two NO3s. And they react to form all the same stuff. And you'll notice everything's aqueous on both sides, which is why there's really no net ionic reaction here. In other words, if you mix these two things together in a test tube or a beaker, you're not going to see anything happen because it's not making a new precipitate or a new gas. All right, when we go to the next page, it gets a little bit more difficult, mostly because, first of all, you have to write the labels here for formula equation, total ionic equation, and net ionic equation. But the second thing is there's going to be a little stuff mixed up in here. This first particular problem, number 1, is actually pretty typical of any sort of these net ionic equations. This is just a plain old double replacement because we've got two compounds reacting. Lead is 2 plus because of the 2 Roman numeral there. Nitrate is 1 minus because it's always 1 minus. Lithium is 1 plus. You can look on the periodic table for that one. And chloride is 1 minus. You can look on the periodic table for that one. They're solutions, so they're both aqueous. You should crisscross the charge on the lead to make sure that it's neutral. So that'll give us lead nitrate, which is aqueous. Will react with lithium chloride, which is also aqueous, to make lithium nitrate, which is aqueous according to the solubility rules. It contains nitrate right up there. And by the way, anything with a group 1 element like lithium or sodium or potassium is always going to be soluble. And then the other one is lead chloride, which finally, chloride is usually soluble, but when it's with lead, it's not. So this is our solid precipitate. Yay, finally we have a precipitate reaction. All right, when we do this all out, we notice it's not balanced. We've got to put 2 in front there to balance it and a 2 in front there to balance it. All right, let's do the total ionic. This is going to be pretty typical. We're just going to start writing the ions. It's 2 plus, aqueous. I told you in class that this was going to be tedious, and in fact it is. The reason I'm writing it all out for you right now is to show to you that even though it is tedious, you do in fact have to do it. If I have to do it, you have to do it. Q. And notice space management becomes quite an issue here because I'm running out of space very, very quickly. So I'm just going to go to the next line. Plus NO3. There's 2 of them, and they're aqueous. Plus PbCl2, which is a solid. Yeah, I probably could have managed that line a little better. I didn't want to write anything to the left of the arrow because that would imply it was a reactant, not a product. When we go to the net ionic equation, we'll notice that the only things really changing here are the lead, which is changing, and the chloride, which is changing, and the lithium and the nitrate are both the same on both sides of the equation. So those just cancel out. Oh, I forgot a charge there, by the way. So I'm going to write the net ionic equation with just the lead and just the chloride. And that'll form our good old PbCl2 solid. And it's balanced, which is really good. It should be balanced at the end if you balanced it at the beginning. When we go to number 3, the interesting thing about number 3 is when you do the formula equation, it's a decomp. I'm just writing the answer here. When chlorates decompose, they actually turn into oxygen gas. So it's going to be 2KCl, which is a solid, plus O2, which is a gas. And by the way, when they decompose, the chloride will be left behind in this ionic compound here. You'll notice nothing's aqueous. There are no free-floating ions. Therefore, nothing is ionic in this equation. There is no ionic equation. There is a reaction, so we shouldn't write no reaction, but there are no ions that are free-floating. So therefore, we can't really write a total ionic equation or a net ionic equation. That one was a lot easier than the previous ones, huh? Number 5, bet you never knew that this was a single replacement because it's an element combining with a compound. You can look up the activity series of the nonmetals. And if you look up the activity series of the nonmetals, you will see that chloride is strong enough to kick out the bromine in magnesium bromide. So when we do this, chlorine gas is diatomic. It's bubbled into a solution. That's our keyword for aqueous, right? Magnesium bromide. Br2 because magnesium is 2 plus and bromide's 1 minus. It's aqueous. And the chloride is going to take its place, and the bromine is going to be kicked out. Bromine is normally a liquid at room temperature. You can look at a periodic table that has colors to see that, or look it up on Wikipedia or some other website to look up the data of bromine. Bromine and mercury are the only 2 elements that are normally liquid at room temperature. Anyway, the other product is magnesium chloride. All right, I want to point out and stress this, that the only reason that there are 2's in all these places is because here it's 2 because it's diatomic, but here it's 2 because magnesium is 2 plus. So don't get it confused. Don't just say, oh, it's automatically a 2, because it's not. That 2's there for a different reason than the 2 is on chloride when it's 1. All right, so total ionic equation. Well, chlorine is a gas. It's not ions. It's 2 atoms that don't have a charge that are bonded together covalently. Magnesium bromide is ionic. It has a metal and a nonmetal in it. So we have to write the ions separate because they are aqueous. Oh, oops, I made a mistake there. You shouldn't put the 2 there. You should put the 2 in front. The 2 down there would imply that they're bonded. They're not. They're now separate in solution. Bromine is a liquid. Should put the 2 on that one. Magnesium is 2 plus, which is aqueous. And chlorine is now both separated because they're both aqueous and they're both charged. So negative charge. All right, you'll notice magnesium's the spectator ion here because magnesium appears on both sides of the equation. So we're just going to write the equation with magnesium. So you'll notice chlorine was 0 for its charge, and now chlorine is -1. So chlorine's actually gaining electrons there. Chlorine's being reduced, whereas bromine was -1, and now it's 0. Bromine's being oxidized. It's a redox equation. All right, we're going to do number 7. I told you earlier in the video that this would be a really typical example of a net ionic equation. So that's why I'm doing this one. So let's go to silver, which is Ag. Silver's always 1+. That's an exception you should know. It's always, always, always 1+, even though it's a transition metal. Acetate C2H3O2, and it's negative. Barium is 2+, and chloride is negative. And they're both solutions, so they're both aqueous. So when we do this thing, AgC2H3O2, which is aqueous, will react with barium chloride. We have to crisscross the charges to make it neutral. That's aqueous as well. To form, well, what does it form? Well, silver's going to go with chlorine, and barium's going to go with acetate. And when silver goes with chlorine, you'll notice chlorine and silver makes an insoluble compound. It makes a precipitate, AgCl, which is just plain old solid. And it's 1+ and 1- for the charges, so no other subscripts. And then our other one is barium acetate. And we have to crisscross the charges. That's where the new subscript 2 comes from there. And that's aqueous because acetates are always aqueous. All right, we do have to balance this thing. There have to be 2 acetates, so we'll put a 2 there. And then there have to be 2 silvers, and lo and behold, the chlorine balances itself. So that there's 2 silvers, there's 2 acetates, there's 2 chlorides, and there's 1 barium on each side of the equation. All right, when we go to the totally ionic equation, remember the precipitate's the only thing that's going to stick together. Everything else will be broken up because everything else in the equation is aqueous. Wow, this is going to be pretty lengthy. But you know at this point that lengthy, tedious writing is pretty typical in these reactions. All right, finally the yields arrow, 2AgCl, which is solid, plus the barium is aqueous, plus the 2 acetates, which are also aqueous. Wow, that was a lot of writing. You'll notice that it's almost like, why did we even do that? Because the acetate is aqueous on both sides of the equation. And if you notice, the barium is aqueous on both sides of the equation. So as a result, when we write the net ionic equation, those just fall completely out. And all that we're left with is Ag and Cl. All right. Now, there's one very, very important thing going on here that we have to point out, which is when you cancel out everything, you get a new equation with the same coefficients as before. But now, what's the ratio? It's 2 to 2 to 2. And that, my friends, has to reduce. So really, you have to write the reduced equation, which is just 1, 1, and 1. So that's the final answer. So, oops, I forgot an aqueous here, and I forgot an aqueous here. All right. So that's the final answer for number 7. Number 9, we're starting to get a little, twitchy here towards the end of the video, right? I'd like to point out that ammonium, NH4, perchlorate's found in rocket fuel, barium, and hydroxide. Well, when that whole thing rearranges in a double replacement reaction, by the way, I'm not even going to write that at this point. I'm getting a little twitchy. But when that rearranges, you're going to form ammonium hydroxide, which if you look up here, will decompose to form water and ammonia. So really the total ionic equation is going to be ammonium, which is aqueous at the beginning, and perchlorate, ClO4, which is aqueous at the beginning, plus barium, which is aqueous, a lot of aqueous things as always, hydroxide, which is aqueous. I'm not even going to concern myself with the fact that that's not balanced with the 2 there. I actually need a 2 and 2 there after we get the final answer. You'll see why. So that's going to form barium, which is aqueous, and perchlorate. Perchlorate's pretty much always going to be perchlorate's going to always be soluble. So ClO4. That's actually why when rocket fuel gets into the groundwater, there's not much way of getting rid of it. All right, ammonium hydroxide is going to split apart as soon as it's formed into ammonia, which is a gas, and water, which is a liquid. That's actually the driving force of this equation. All right, we need 2 of these to balance out the barium, and then in order to get those 2 perchlorates over here, we needed 2 ammoniums, and that's why we're going to get 2 and 2 here and here. And so now everything's balanced. If you don't know why I put all those 2's in there, you really should write the formula equation to see where they came from. Sorry, my explanation isn't that good. Like I said, twitchiness. All right, you might notice now that really the barium and the perchlorate are not really doing anything. So as a result, the net ionic is only going to have the ammonia, the ammonium, the hydroxide, the ammonia, and the water. And you'll notice that the coefficients on all those things are 2's, which means the net ionic equation just should reduce to 1's. All right. Interestingly enough, I just lost my thought. Is there really anything interesting about this? Oh yeah, interestingly enough, this is not a redox equation. Everything has the same charges left and right, or fake charges in the case of these molecules here. Molecules, you know, don't have charges, but we can pretend they have charges and everything actually still has the same oxidation state as before. So this is not a redox equation. This is a metathesis reaction, or a combination reaction. I'm not really sure which at this point, but we will talk about it in the very near future. That's it for me.